Hey everybody, we're going to look through some multiple choice questions regarding conservation of energy here. So let's look at the first one. It says we got a pendulum that's launched in two different ways. During both launches, the bob has an initial speed of 3 meters per second. Launch 1, the speed is up, and launch 2, the speed is down. So you can see that in the image over here, right? We have, this is my initial point. V1, that's launch 1, is being launched upwards, so tangent to the motion or perpendicular to the string there. So it's being launched up with 3 meters per second. And in the second launch, it has exactly the same speed, right? Noticing that it's equal to negative V1, 3 meters per second, down in the opposite direction. So then the question is, which launch will allow it to have the largest angle on the other side? Well, hopefully you are recognizing that in both situations it starts at exactly the same height. Now that's significant because that means it's going to start with exactly the same gravitational potential energy. Now we're referring to the system of the ball and the earth. So it has a certain amount of gravitational potential energy in that system. So in both situations, whether I throw it up or whether I throw it down, it has the same MGH, or the same gravitational potential energy. So EP1 equals EP2, right? And this is the initial, of course. Now, we continue to look at the kinetic energy. So the kinetic energy at the starting point, again, is the same, right? It has the same speed at the beginning, 3 meters a second. It doesn't matter if it's up or down. The kinetic energy is the same. And so the kinetic energy, so EK of 1 must equal EK of 2. And again, this is initial. Now, if the potential energy and the kinetic energy are equal at the beginning, then that means that the total energy of the pendulum is the same at the beginning. What that means is that at the end, it must end with the same final energy, which means both launches must give the same maximum displacement. Now, if there's air resistance, then obviously our answer would be a little bit different. If we consider air resistance, then the pendulum that swings further would have more air resistance, so it would have more of a chance to lose energy, right? Remember that work is equal to force times distance, or force times displacement. So if it travels further, then it's going to actually have more air resistance. It'll lose more energy, more work will be done on it, and so therefore it won't go as high. So our answer is going to change based off of that. So if there's no air resistance, the answer is that they both go the same angle. If there is air resistance, then the one where it's swung down, launch 2, would have a larger distance just because there will be less air resistance there. Okay, awesome. Let's look at concept test number 8. A mass M is at the end of a light massless rod of length r, the other end of which has a frictionless pivot so that the rod can swing in a vertical plane. So it's swinging just like, this is a side view. We're seeing the rod swing down, kind of like a pendulum, but in this case, it's going to swing all the way up to the top. The rod is initially horizontal, and the mass is pushed down with initial speed v0. So what initial kinetic energy is required for the mass to pivot all the way up to that 12 o'clock, 270 degrees, right from here around to there would be 270 degrees. So how fast do we need to push it? All right. Well, there's a couple of ways to go about this, but I would say we're going to simplify. We're going to call this initial height right here. This is going to be my height equals 0. You can define where you want your 0 height to be. Now, can you define the bottom to 0? Yeah, but we don't need to, because no part of our question is below that point. Yeah, it swings down there, but we know that energy is conserved the whole time. The only forces here are gravity pulling down, and then the force of the rod, which is causing the mass to go in a circle. But that's always towards the center of the circle. That's always perpendicular to the motion. Remember, perpendicular forces don't do work. They don't add in or take out energy. And so I'm going to define this as my height 0, which means in the beginning there is no height. There is only the kinetic energy. So in the beginning we would only have 1/2 m V initial squared. And that's what we start with. In the end, I want to end up here. I don't need any speed. I need to just barely have enough speed that it gets just up to that point, and then it answers the question, right? Any more speed than that means that it'll continue to have speed at the top. But this is going to be to find the limit. And we actually do this quite often, is find the limit between when one thing happens and when something else happens. So here, it's just going to be the mass times g times the height, which at this point, the height, you'll notice, is the radius, because that's how high the mass will be. And so now we should be able to solve for the initial kinetic energy. Recognize here that it's asking for the initial kinetic energy. It's not asking for the velocity. So the initial kinetic energy is this part right here. This is the initial kinetic energy. So because that's the initial kinetic energy, then that's going to just be equal to mgh, or in this case, of course, mgr. And so that's all I need to find is mgr. And so I would go for this one right here, mgr, and that would be my final answer, letter A. All right? Doing all right? Okay, let's keep going. The last question here, we have a cart that rolls without friction on a track. Okay, remember on a track, the only forces then are gravity and the normal force of the track. The normal force of the track is always perpendicular. And so we're going to look at this question. We'll say it rolls, the graph of gravitational potential energy versus position is shown. So this shows my gravitational potential energy. So I'm going to label that as the gravitational potential, the EP there. That's what we use in IB. If you're in AP, you might use something like this. That's what they usually use for potential energy. So you might see that at some point in time. Even if you're in DP IB right now, eventually in university you might see notation such as that being used. The total mechanical energy, kinetic energy plus gravitational potential energy, is 45 kilojoules. So you can see that that's labeled right here at the 45. That's our total mechanical energy. That's the kinetic energy plus the gravitational. And that is at 45 kilojoules. To within 5 kilojoules, what is the maximum kinetic energy over the stretch of the track shown? Now, obviously, we could draw a graph of this, and I would be interested in doing that. I'm going to go ahead and do that, but I'm going to answer the question first. Let's answer the question first. Once we've answered the question, then I am going to go back and draw the graph of the kinetic energy in case you're interested, in case you want to see that. That's a good thing to be able to do, is to be able to take one graph and draw another graph from it. All right? But what I want to do right now is just answer the question. The question is, when is the maximum kinetic energy? In order to get the maximum kinetic energy, we need the gravitational potential energy to be the lowest, right? It tells us right here the total mechanical energy is the kinetic energy plus the gravitational. So if the gravitational energy is lower, then the kinetic energy will be higher. So I find my lowest gravitational potential energy right here, which is at 10. And then you can tell that the rest of that energy to get to the total must be kinetic. So 45 minus 10 is 35. And so I'm going to find something that's close to 35. It does say within 5 kilojoules. My guess is that it looks like the curve doesn't quite touch down to 10. So maybe it's actually at 11 or something like that. And so it's close enough. Within 5 kilojoules, I think A is going to be the correct. It's obviously the closest of all of them, and it's within 5 kilojoules. So I'm going to go with A for my answer on this one. Now, I do want to go ahead and draw the kinetic energy graph. What I would do on this is I would just take individual points. Don't try to just free sketch it. Okay, like this point right here looks like, the first point right here looks like it's at about 33, 34. And so I would subtract that from my 45, and so that would be about 12. So I would say that my kinetic energy should be down here somewhere, right? This point right here, I'm going to take the next significant point. That's at about 21. So 45 minus 21, that's going to be 24. So that should give me a graph right around here, right? Then I'm going to take the top point here. The top point here is almost up at 40, but not quite. Looks like maybe I'd have about 7 left there. And you can do 45 minus 38 or whatever you decide it is. But it looks kind of like that. And then, of course, we just came up with this point right here. We said that that was about, if it's at 10, it's somewhere up here, about 35. So the kinetic energy should be up there. Another interesting point would be, we know that there's 45 kilojoules if there's 45 kilojoules, then that means when the gravitational potential energy is at half, when half of it is gravitational, half of it must be kinetic as well. And so if you find that 22.5 and you put just kind of a dashed line there, so that's my 22.5, anywhere where the line crosses that, where the gravitational potential energy has that value, the kinetic energy must also have that value. And so that'll kind of give us one final thing. And so I'm just going to kind of try to draw as best I can, go up to that point, go down to this one. Okay, notice that I'm crossing at those places, right? I'm going to make sure that when I come up here, I cross through there, and then I go up through there. And then the last, I should have looked at this one as well. So that one's at about 18. So 45 minus 18 is about 27. So I got to make sure to end somewhere around 27. So something like that. And so you can see my yellow graph here then has my kinetic energy, EK. And so there. Now I've been able to draw a graph of that. And it does correlate with the answer that I gave before. All right, so hopefully that's helpful. Watch the next video for some more practice if you would like. All right, in this next video, we'll be looking at one multiple choice question and two free response questions that deal with energy here, all right? So constant test number 10, we've got a small mass that's sliding at rest, going without friction down a rail to a loop-the-loop is shown. The maximum height of the loop is the same as the initial height. We can see that with the dashed line up here at the top. And it says, will the ball make it to the top of the loop? All right, now this one is really, really tempting because especially since we're doing we're doing energy right now, it's really easy for us to think, well, it starts with this much gravitational potential energy, so it should be able to end with that amount of gravitational potential energy. Well, the problem is, in order for it to be going in a loop, it needs to have some kinetic energy, right? If it doesn't have kinetic energy, even if it could get up to the top at this point, all of the energy would be potential. It would have no kinetic energy, and it would just drop straight down. Now, that doesn't actually happen. It doesn't actually go all the way up to the top and then decide to stop at the top and then fall down. What actually happens is as it comes down, as it gets to this point, it's losing its kinetic energy. In order to stay in this loop, remember circular motion is that the centripetal force equals mv squared over r. If your v is not high enough, then the centripetal force is likely going to be too strong, and so it's going to pull you down much quicker. So gravity is pulling us down. If as I go up, as I get to this point right here, if I'm not going fast enough, then gravity is going to pull me down quicker, right? Because my velocity is lower, so my centripetal force needs to be lower. But gravity doesn't change dependent on our velocity. Gravity is the same strength no matter what. So as my velocity here decreases, that means that the gravity is too strong to be a centripetal force, and it actually pulls my my ball off of the track. It's not going to make it all the way up. Okay, so that's one way to think about it. There's other ways to think about it, but I hope that kind of makes it clear. Number one, it doesn't make sense for it to go all the way up to the stop and then all the way up to the top and then immediately stop and fall. It should make sense that as it's going up, it's slowing down, and it has to have that kinetic energy. If it doesn't have the kinetic energy at the top, then it shouldn't be getting there anyway. Okay, let's go on. Let's look at a free response. We've done a couple of multiple choice now. So a pendulum of length 1 meter is released from rest with the string at an angle of 10 degrees to the vertical. Find the speed of the mass and on the end of the pendulum when it passes through its lowest position. All right, so we've got a pendulum that has a length of 1 meter. Okay, it's starting with an angle of 10 degrees. And then we have the pendulum later, which is at its lowest point, right? That's what it wants to find the speed of the mass through its lowest position. So that's 10 degrees right there. So we have our pendulum down at the bottom. All right, the radius is still 1 meter. All right, the question is we need to find the velocity at this point. So starting up here, it's going to swing down this way, and it is going to have a velocity moving to the right. Okay, so let me get rid of that. So it is going to be swinging to the right. That's what we're looking for. Now, hopefully what you're thinking about is you're thinking about that demo we did in class where I started the mass at a certain height. It swung down from in front of my face. At the bottom of its swing, it had kinetic energy. It lost all of the gravitational potential energy that it's going to do. It swung up, and then it came back. But at the bottom, that's where it had its maximum potential, maximum kinetic energy. That is where all of my gravitational potential energy, right? We had some height here. The height from where I dropped it from all the way down to its lowest point. That change in height is what is going to determine the kinetic energy at the end, right? And so at the beginning, we would have gravitational potential energy. So we would say mgh at the beginning. And then at the end here at the bottom, we would have 1/2 mv squared. Now that's because I'm defining this to be height 0. And so at the end, it wouldn't have gravitational potential energy. If you wanted to say it's a couple of meters off the ground, that's fine. But then this height right here would need to include that couple of meters off the ground as well. So just simplify, make this height 0. And then initially it has gravitational potential energy with the system of the Earth, of course. And then at the bottom of the swing, it would then have its kinetic energy. So now I'm trying to find V. We do notice that it does have mass on both sides, so let's just divide by mass. It wasn't given to us in the question, right? But what I'm missing here is that height, right? That's what I need. And so we're going to go through. We need to do some math here, all right? You'll notice that if I use this parallel line, then it creates a right angle here, all right? Now I have the hypotenuse of my right angle. And so with the hypotenuse and the angle, I should be able to find that right there. Okay, so I'm going to do 10. I have the hypotenuse and I want the adjacent side right here. So I'm going to go cosine of theta is equal to the adjacent over the hypotenuse, just like that. Okay, now I'm going to go ahead and calculate just cosine of 10, because it'll be cosine of 10 times 1. So if I go cosine of 10 on my calculator, I get that x equals 0.9848 meters. Okay? Now, you might think that that seems really close to 1 meter. You're exactly right. Go ahead, sometime take a pendulum and raise it 10 degrees. Just do 10-degree angle, right? That's 1/9 of a right angle. So it's not a very large angle. So if you swing it that high, look at the difference in the height of the pendulum. It's not very much. It's there, but it's not very much. Okay? Why this is significant is because that number now is this height. That's not what we're looking for. Don't put that in for H, right? What we're looking for H is this delta, the change in the height. So that would be the full 1 meter of the string minus the 0.9848 that we just got. And so what we end up getting is that our height, or the change in height, however you want to look at it, is 0.0152, just like that. All right, so we're going to put that in for the H. We've got G, so I'm going back to my original equation here. Okay, so G is 9.8. The height is 0.0152. That's going to be equal to 1/2 times V squared. And so let's go ahead and calculate that. So times 9.8. Then I'm going to multiply by 2 to get rid of the 1/2. And then I'm going to square root it. And my final answer is that I get V equals 0.545. I'm looking at my data though. I've got 2 sig figs here. This is actually only 1 sig fig. So my final answer, I'm actually just going to go V equals 0.5 meters per second. There you go. We got the speed as it passes through its lowest position. Not bad, given that it only started a couple of centimeters up, right? So it's already going pretty quick. All right. Great. Let's look at another one. Let's move on to example number 4. Okay. In example number 4, we have 2 identical balls that are being launched from the table at the same speed. One ball is thrown vertically up and the other vertically down. The height of the table from the floor is h. Predict which of the two balls will hit the floor with greater speed. First, consider the situation where there's no air resistance. So hopefully, after we did the pendulum question in the previous video, this is pretty straightforward for you. Hopefully that you're noticing that they are starting at the same height. So they start with the same MGH, right? And you're noticing that they both start with the same speed, right? It says they're identical balls with the same speed. And so therefore this one is being thrown upwards, that one's being thrown downward. It doesn't matter because the 1/2 mv squared is the same for both of them. So therefore, which one will hit the ground with the greater speed? Well, they will hit the ground with the same speed, right? Because they started with the same amount of energy. Therefore, when they get down to the ground, they must end with the same energy. That's as long as nothing is doing work, as long as no energy is being put in or taken out. Okay? Now, the second question is slightly different, but we talked about this with the pendulum as well, right? We said, okay, how would this be different if there is air resistance? Well, remember, work depends on force and displacement. And so as you travel further, as you go a longer distance, you're going to be taking out more energy, right? And so in the situation where the ball goes up, it's losing energy all the way as it goes up. And then as it starts to fall down, it's going to be losing energy all the way down as well. And so you actually have much more distance over which that force is being exerted. And so therefore, you're going to lose significantly more energy. All right. This one only loses energy as it falls. So therefore, which one will hit the floor with greater speed? And this one, the one thrown down, will have greater speed. All right, that's it. Hopefully that was helpful. Those are a couple of good questions. Let's move on and try some more. Hey everybody, we're going to look at a couple more conservation of energy questions here. The first one, we have a bowling alley and we have a ball that's at the bottom. The ball feeder mechanism is going to push it up the ramp there so that it gets up to the top. It does give us the length of the ramp, and it also tells us that the ramp is 0.5 meters, or sorry, the chute is 0.5 meters above the base. And so the question is, how much force do we need in order to get our bowling ball up to the top? All right. Now, hopefully you're thinking about conservation of energy here. You're seeing that there's a force causing the ball to gain energy. You're seeing that it's going up, which means it's gaining gravitational potential energy. So let's look at total energy here, right? Now, before, when we did conservation of energy, we said initially that the sum of the energies in the beginning had to be equal to the sum of energies at the end. Now, that's only the case if energy is conserved, if no work is being done. But the chute here is going to be exerting a force on the ball going upwards, which means there will be work done. And so we do need to modify our equation slightly. So in the beginning, we're still going to have a certain amount of energy, but then we're going to add in the energy done by work. Now, if the object is taking energy out, we'll get a negative work, and that's fine. But in this situation, we know it's going to be adding energy in. And so when I take my initial and add the energy in, that should give me the total energy at the end. All right, so let's talk through what types of energy do we have at the beginning and the end, and then we'll talk about the work, the force being done in between. So at the beginning, I'm going to go ahead and define this as being height 0, right? That's the lowest it goes between my initial and final points. So I'm going to say that that is my initial height, which means that the ball Earth system has no gravitational potential energy at the beginning. We're also going to assume that there's no kinetic energy, because if it has kinetic energy, then the mechanism will need to do less work, right? If it already has some energy, it'll be easier for the mechanism. So we're going to assume the most difficult situation so that we know that 100% sure our mechanism will be able to get the ball up to the top. And so we're going to go ahead and say it doesn't have any kinetic energy at the beginning either. So no kinetic and no gravitational potential at the beginning. So the total energy at the beginning is 0. All right. Now, as it goes up, the mechanism is going to exert this force on the ball for that distance. All right? And so remember that work is force times distance. Now, there is an angle associated with that, but in this case, the force is up the ramp and the displacement is also up the ramp. So I don't need the angle. They're already parallel to each other. All right? Now, the energy at the end, now we're up here. Again, I don't need kinetic energy, right? It's tempting to have some kinetic energy up there, but if I have zero kinetic energy, that's fine. I still get to the top of the ramp. Okay? I will, though, have gravitational potential energy, right? And that will be based off of the height, which it did tell me. They could have just given me an angle here and I could have figured it out, but they did tell me that the height was 0.5 meters. All right? So the final energy, no kinetic energy there, is going to be completely based off of M, G, and H. All right? So the force being exerted, that's what I'm looking for. The S is the distance over which that's exerted, which we said was 1 meter. The mass of the ball is 5. G, of course, is 9.8. And the height, as given, is 0.5. So notice that the distance and the height are different values. That should be okay, right? The distance is the distance up the ramp, whereas the height is just the vertical height. That's the only thing that affects the vertical force of gravity, so therefore the gravitational potential energy. So I put all this together, I multiply the 5 times the 9.8 times the 0.5, divide by the 1, and I do get a force of 24.5 newtons. Now, I do want to make sure that I put the answer in the right number of significant figures. I've got 2, oh snap, that only has one significant figure. So my final answer, as IB would like it, is 20 newtons there. All right, so there we go. 20 newtons is our final answer. And that's it. All right, let's have a look at example number 6. Now, I love these ones. I love the ones where we get to do multiple methods. All right, now, technically, we probably could have done multiple methods here, right? You probably could have done something with kinematics and going up the ramp, and you might have been able to do something with that, but we didn't. So here, let's go ahead. This time I'm going to ask you to do both. We have a 200-gram ball that is lifted upward on a string. It goes from rest to a speed of 2 meters per second and a distance of 1 meter. What is the tension in the string? All right, so let's go ahead and let's do dynamics, kinematics first, right? And so let's list out our SUVAT, S-U-V-A-N-T. I know it starts at rest. I know that it goes to a speed of 2 meters per second. It says my distance is 1 meter. And so, yeah, so I'm looking for tension. So I'm probably going to go ahead and go with acceleration. Time isn't going to matter here. So I need SUVANT. So that looks like I'm going to need the equation V squared equals U squared plus 2AS. And so the V squared, that'll be 2 squared equals 0 squared plus 2 times A times 1. And yeah, so I'm going to get 4 equals 2A. I'll divide by 2, and I'm going to get the A equals 2 meters per second squared. All right, very nice, no problem at all. So we got A, and now we are going to go force equals MA. But be careful here. It's not just F equals MA. It's the sum of the forces equals MA. Because we do have the ball that is on a string, right? So we have 2 forces going on there. We have the force of gravity pulling down, and then we have the tension, which is pulling up. Now, because it's being lifted upwards, the tension must be greater than the force of gravity. If they're equal, it would go at a constant speed, but it's not going at a constant speed, it's going faster. All right, so I do need some of the forces here. So instead of just putting tension there, I need to put tension minus the force of gravity. So tension is up, force of gravity is down, and then the acceleration was upwards. And so now I can put those numbers in. I can go tension minus the force of gravity, which is mg. So I'm going to go ahead and just put in the 0.200 times 9.8 equals the mass, which was 0.200, times the acceleration that I found in the previous question, which is 2, right? So if the two forces were equal, if the tension was equal to the force of gravity, I would have 0 acceleration. In order to have acceleration upwards, my tension needs to be even bigger, right? So at this point, I can take my 0.2 and multiply by the 2, and then I'm going to add the 0.2 times the 9.8. So I need to have something slightly larger than gravity there. And so I do end up getting that I have a tension of 2.36. I only have one significant figure in both of those, and so I'm actually just going to go T equals 2 newtons, just like that. All right, so we got the tension in the string. Let's see if we can do that using work and energy now. Okay, again, for energy, we're going to be looking at the ball and earth system, so we can include gravitational potential energy. So again, just like in the previous one, we're going to do sum of the initial energies must equal sum of the final energies. But because there is work being done, right, the tension here is going to do work because the tension is pulling parallel to the direction of the motion. It's causing it to accelerate, right? It's going up and it's gaining kinetic energy, which means we have to be adding some energy into the situation. So we are going to modify this slightly. Instead of this, we're going to go sum of the initial energies plus the work being done needs to equal the sum of the final energies. All right. Now, in the beginning, it says that it's at rest, which means that its EK equals 0. It's also at its lowest point, which means that the gravitational potential energy is also 0. So in this situation, again, similar to the last one, I'm going to be able to say that the initial energy is 0. Then I'm going to add on the work. Now the work is going to be the force times the distance. So what force does the tension have to? This is the work. We're looking for the tension in the string. So I want the force in the string. So I want the work done by tension. So I'm going to end up putting the force being tension and the displacement being 1 meter. And then on this side, I'm going to have the final energy. Now, at the end, it's going to have some kinetic energy, right? Because it's going to have that 1/2 times the mass times the v squared, because we know it has some speed there at the end. But it also has some gravitational potential energy, mgh, because its height has changed. And so now at this point, we should be able to put in all those numbers. And so we're going to go t times 1 is t, equals 1/2 times the mass times the velocity, which is 2 squared, plus the mass, which is 0.2, times 9.8, times the height, which is 1. And I know what you're thinking. You're thinking, there's no way that's going to give me the same thing. But if you take 0.5 and you multiply it by 0.2, and then you multiply it by 2 squared, which is 4, and then you add 0.2 times 9.8 times 1, then you actually do get exactly, isn't this nice? We get exactly the same thing. T equals 2.36, which again, 1 sig fig, I'm going to say T equals 2 newtons. And look, we got the same thing. Woo, doggy. All right, that's it. All right, y'all, in this video, we're only going to look at one example. All right, so we've got a body of mass of 2 kilograms that's initially at rest, which is sliding down a curved path of total length 22 meters. Now, it says as shown in the image. I don't see an image here, so I'm going to have to draw my own. So curved path, the total length of the path is 22 meters. The mass is starting at rest, and it is 2.0 kg. The body starts from a vertical height of 5 meters. All right, so I'm going to go ahead and just mark that as being 5 meters. It is 5.0, okay. When it reaches the bottom, the speed is measured and found to equal 6 meters per second. Okay, so the velocity at the end is 6 meters per second. All right, I am noticing that they all have 2 significant figures. That's nice. That means in the end, I do need to have 2 significant figures, all right? So I'm going to mark that down. I'll remember that later. Okay, show that there must be a force resisting the motion. All right, so the way I'm going to do that is I'm going to say, well, if there was no force, what would happen? Well, if there was no force, then the sum of the energies initial should equal the sum of the energies final, right? Now, the energy initial would just be between the block Earth system, it would be gravitational potential energy. So that would be mgh. In the end, it would be the kinetic energy, right? At the end, we're down to height 0, and so it would just be the kinetic energy, so 1/2 mv squared. Now, if we put that together, we should get that the masses cancel out, so the mass didn't matter anyway. The g would be 9.8, the height would be 5, then we'd have 1/2 times the final velocity, which is 6 squared, and so if I do 9.8 times 5, then I get 49. But if I do 1/2 times 6, 6 is 36 times 1/2, that would give me 18. Holy smokes, there's a problem there, right? My final kinetic energy is not equal to my initial kinetic energy. Because of that, that must mean that energy was lost. The only way to lose energy is if there is a force resisting the motion. And so that right there is proof, because the initial is not equal to the final. If this was an exam, I'd write it out, but because it's not an exam, I'm just telling you. But that would be proof that there must be a force resisting the motion. So we move on to part B. So in part B, we are assuming the resistance force to have a constant magnitude, and so we're going to determine the magnitude of the force. Well, this is going to go into what we were doing before. We're going to say that the initial energy, but this time we know that there's some work being done. It's okay, just put a plus work there, that's fine. Must equal the final energy. Now, I've already done a lot of this work already, right? I know that the initial energy was 49. Okay, the work is the force times the distance. Okay, and then the final energy, I already calculated as well, is 18. And so when I do the 18 minus the 49 and I put in my distance, then I'm going to have the force times 22, because that is the length of the ramp, right? The resistance force obviously here is friction. That's the thing causing me to lose energy as I slide down the ramp. And so I need the distance over which the friction takes place. And so that's going to be 22 meters, not the height. The height is just the vertical change, but we need the whole distance over which that block travels. And so we're going to put in 22 for that. And then 18 minus 49 would be negative 31 there, right? And so now we take that negative 31 and we divide by 22, and we get that the force is equal to 1.4 newtons. And it is negative because it's opposing the motion. So there we go. We found the resistive force, assuming that it had a constant magnitude. Now, the last question here is, well, is it a good assumption that the resistance force has a constant magnitude? Hopefully you said no, right? Why? Because the normal force is changing. Now, because the normal force is changing, we know that friction depends on the coefficient of friction times the normal force. So if the normal force is changing, then friction must also be changing. I'm going to just write a delta. So if the normal force is changing, the friction must also be changing. So therefore, the resistive force should not be equal. That should kind of make sense. I mean, here at the beginning, the block is really just kind of dropping almost. There's not a lot of friction there. But as we get further down at this point, the block is being pushed down into the ramp a little bit harder. There should be more friction there, right? Now, it does say the body of mass is sliding. It doesn't show what it is. I drew a block, but even if it was a ball, it would say that it's sliding. The reason why is because initially if we assume there's no resistive forces, then the ball won't roll. In order for a ball to roll, there needs to be some friction, right? The friction on the bottom of the ball is what causes the top of the ball to rotate faster than the bottom of the ball and then allows the ball to roll. The second problem with rolling is that if it's rolling, then some of the energy has been put into rolling. And that may actually be the case with why we're losing so much energy here, is because if there is friction, some of the energy is going into just heat due to the friction and the rubbing with the ramp, but some of the energy is likely going into the ball, causing it to spin as well. And so we've lost a significant amount of energy there, a significant amount of translational kinetic energy and gravitational potential energy, because that energy has gone into other places. All right, so that's kind of interesting, I think. All right, I wanted to make sure we had an example question that had a spring in it as well, so let's have a look at that. We've got a mass of 4.2 kilograms that has an initial speed of 5.6 meters per second. It's going to start to go up an incline. The body will be brought to rest at the top of the ramp by a compressed spring. So we want to determine how far the spring will compress. All right, so let's draw a picture first. Okay, so we've got our ramp. We've got our 4.2 kilogram body that's moving up. Okay, we are going to assume no friction because we don't have enough information to be able to deal with it, right? Unless there's something that asks us how much friction there was or whatever. We're gonna assume that the ramp is smooth, that there's no friction there. So it's moving upwards with a speed of 5.6 meters per second. As it goes up, it says that the ramp is 0.85 meters tall. So that's going to be important here, 0.85 meters tall. And then at the top, it's going to hit a spring. And the question is, how far is the spring going to compress? Now, when it gets to the top, it's going to be brought to rest, which means when it does get to the top, the velocity is going to be 0. All right? So at this point, we're going to have to consider all our types of energy, right? At least all the types we've talked about so far. So at the beginning, we have kinetic energy, right? So we're looking at sum of the energies initial must equal sum of the energies final. Now there's two ways to look at this. You can look at the spring as an external force. You can look at it as internal. I'm going to start with assuming that it's an internal force, okay? So in that case, at the beginning, I definitely have kinetic energy, right? There's no gravitational because I'm at 0, and there's no elastic energy yet either because I'm not interacting with the spring. So we're going to include the spring inside. So that's the only energy to start with. In the end, when I come to rest with the spring, I'm going to have 0 kinetic energy, but I am going to have potential energy because I'm at the top of the ramp now. I'm up at this new height, and I'm also going to have the elastic potential energy of the spring. Remember, they use EH because the spring compressing is due to Hooke's law there, okay? And so that's what we got. And so we're going to go ahead and put in the numbers that we have. Recognize that because we said there's no friction, there's no work being done. All the forces that are happening here, the normal force is perpendicular, gravity and the force of the spring are both internal. They're both conservative forces. We can account for them with our conservative energies here. All right, so we go 1/2 times the mass, which was 4.2, times 5.6 squared. And that needs to equal my gravitational potential energy, which is going to be the mass, 4.2, times g, which is 9.8, times the height, which is 0.85. And then I'm going to add on the elastic potential energy, which is 1/2 times k times x squared. And x, remember, is the compression of the spring. Just like that. All right. So with this, we actually have enough information that we can solve for x. We can finish the question just like that. So I plug all that in my calculator, 1/2 times 4.2 times 5.6 squared. Then I'm going to subtract off the 4.2 times 9.8 times 0.85 because I need to move that over. I'll multiply, so I'll get all that. I'll multiply by 2 divided by 1,000. That'll be equal to x squared. And in the end, I should get, and you should try this on your own, don't trust me, you should get that x equals 0.25 meters. Now, I've written it in two significant figures because most of my things here are in two significant figures. You could debate that maybe it should be 1 because of the spring constant there. Go ahead, you can debate it. I'm just going to write 0.25 meters, and that's it. That's the end of the question. Now, it is really tempting because I did get excited on some of the other ones where I was able to show you different ways of working through a question. It is tempting to say, well, can I make the spring be an external force? Can I make that be an outside force? So as the block comes up, I have kinetic energy at the beginning. It goes up, it gains that potential energy, and the spring is an outside force. The spring is doing work, force times distance, causing it to lose energy. That is tempting, but unfortunately, as we compress the spring, the force of the spring is going to be changing, right? The more you compress the spring, the stronger the force is. We know that the force of a spring is kx, and x is the distance that's been compressed. So the more you compress it, the stronger the force is. Because the force is changing, then we wouldn't be able to find the work done by the spring. And so in this situation, really considering the spring to be part of the system and doing elastic potential energy is the best way to do this. At least until you learn calculus and you learn how to deal with changing forces and changing acceleration. Remember, that's why Newton created calculus, was so that he could deal with situations with changing forces, changing accelerations. That way he could do more physics, right? So anyway, that's the answer to the question. I hope that was helpful. I think it's a great question, and hopefully we'll have time to look at example number 13 in class sometime. All right, see you later.